In this next video, we're going to apply the first derivative test to functions involving roots and fractional exponents. So these are going to be a little more challenging than the polynomials. So the derivatives will probably be a little bit more difficult, and the equations we need to solve are going to be a little more involved. Otherwise, the process is going to be pretty much the same. So we want to find the relative min and max and the absolute min and max over the entire domain of the function. So with this fractional exponent, if you notice, it's a cubed root. The denominator here is a 3, so this is a cubed root. So there are no problems. You're not going to get undefined values for the function. So it's actually defined for negative infinity to infinity. Also, notice the end behavior as you go off to negative infinity or infinity. So if you go off to negative infinity, this is going to, if it's a negative number, this will square it and then take the cubed root, and that'll be positive. And this will end up being, this term will be negative, and so you'll have a positive times a negative, and so the thing, as you go from off into negative infinity, this is going off into negative infinity. So as x goes to infinity, both of these will be positive, so it'll be going to positive infinity. So this thing is going to take on every value. It's going to go from negative infinity to positive infinity, and so there are no absolute min or max. So what we're going to do is use the first derivative test to find any relative min or maxes. So let's go ahead and do that. What we need to do is take the derivative. Notice this is a product of two functions, and so we're going to need to use the product rule, or you can distribute the x to the 2/3 over both terms, and then you could use the power rule on the two terms. I'm going to go ahead and use the product rule. So I'm going to take the derivative of the first function times the second function plus the first function times the derivative of the second function, which is just 1. So you get all of this. So what I'm going to do is I'm going to simplify this derivative here. So this is a negative exponent, so I can bring this down. So this first term would look like this. Then I'll have 3 on the bottom and x to the 1/3. Okay, and then this is just plus x to the 2/3. Okay, so now what I want to do is I want to combine these over a common denominator. And so when I do that, I'm going to multiply the top and bottom by x to the 1/3 here, and well, top and bottom by 3 times x to the 1/3. And so what I'm going to do, that's going to make this a complete x. So when I do this, I get this. This ends up just being 3x, like that. And then all of this is over 3x to the 1/3. And so now I'm going to distribute the 2 and combine like terms. So that's going to be 5x plus 10 over 3, and then this is really like the cubed root of x is what that is. That makes it look a little, maybe a little less confusing. That fractional exponent never looks very friendly. Fractions are bad enough, fractional exponents even worse, right? So now what we want to do is find the critical points of the function. Well, the way that you solve, well, let me set this up as an equation. It would look like this is equal to 0. So if you have a fraction set equal to 0, it will be equal to 0 whenever the numerator is equal to 0, as long as that value doesn't make the denominator equal to 0. Okay? So really I just need to solve 5x plus 10 is equal to 0. And when I do this, I get x is equal to, bring the 10 to the other side, divide by 5, I get negative 2. So my x is equal to negative 2. So this is a critical point. Now you also have critical points when the function is undefined. And in this case, if x is equal to 0, the function will be undefined. The derivative will be undefined. So f prime of 0 is undefined. And so x equals 0 is another critical point. Okay, so the critical points are when the function is equal to 0 or when it's undefined. So these look like the only two critical points of my function, so I'm going to set up my table. So it looks like I'm going to have like negative infinity to negative 2, and that's at this critical point. And then you're going to have negative 2 to 0. That would be at this critical point. And then you're going to have 0 to infinity. These are the intervals. Okay? Now, this is the derivative. I have no idea how that derivative is going to behave. So I'm just going to pick test points here. So, I don't know. One thing that you can pick any test point as long as it's in this interval. I'm going to pick a negative 8. And the reason I'm going to do that is that makes this kind of nice, because the cubed root of 8 is negative 2. You don't have to do that, but I'm going to do that. And then what you get here is, this would be, well, you could just plug it in, but that'll be negative 2 and that'll be negative 8. And when you do that, this thing, I've already done it over here, is 50 over 6. And so the derivative is positive. Okay, so here, I don't know, I'd probably put in negative 1. And then the derivative at negative 1, when you put it in here, is negative 5/3. That's what I get. And so the derivative is negative. And then here, I'm going to put in x is equal to, I'll just put in 1. Okay, because 1 gives you a cubed root down here. So it'd be 15 over 3, which is just 5. So f prime of 1 is equal to 5, and that's positive. Okay, so what you see is the derivative is positive, and then negative, and negative, and then to positive. And so the function is increasing, and then you have a critical point, and then it's decreasing, and then here, I'm not sure exactly how it is, but it's undefined here, so it's not like 0, but it's doing something like that. Okay, but that's not exactly how it is. Oops, but actually, it can't be doing that because this is positive. So it's doing like this, negative, and then positive, something like that is what it's doing. So negative and then positive, and this is. And it doesn't matter. You don't have to draw what this is going to look like. But this critical point is where the function's undefined. Okay? But it doesn't matter if it's a critical point where the derivative is 0 or undefined. If it switches from negative to positive, it's going to be a min. So x equals negative 2 is a max, is a relative max. and then x equals 0 is a relative min. And neither of these are going to be absolute min or absolute max over the entire domain because this function has no absolute min or max. So let me go ahead and graph this and see if indeed we are correct. So there's the function here, and I'll hit graph, and it looks like this. It kind of curves up, and then there at -2, so if I hit second calc value, put in -2, we see that's where that max is. That's a relative max. And then here at 0, you get the relative min. Okay? And really, the way I knew to draw this, I knew that it was going to look like that because I already had done the problem and I had graphed it. I really would have not known for sure exactly how this would have been. But the nice thing is, it doesn't matter whether it's a critical point due to the derivative being 0 or undefined. The sign change will end up, if it goes from negative to positive, it will be a relative min. If it goes from positive to negative, it will be a relative max. And then you can see it goes off to infinity either direction, so there is no absolute min or max. Okay? So let's do another one. And now this involves involving a root here. Now notice that this function, you can't have a negative underneath a square root. And so this function, the domain, is going to be from -3 to 3. And that's a closed interval. And this function is continuous on the closed interval and differentiable on the open interval. But it is continuous on the closed interval, so it will obtain a min or a max on this closed interval. And it'll either be at a critical point or at the endpoints of this interval. Okay? So what we're going to do is we're going to find the derivative here. So I'm going to use the product rule in this case. Let's see. So the derivative of the first function is just 1 times the second function, and I'll go ahead and write it with an exponent like this, 1/2. And then this is plus, then I have the first function is just an x, and then the derivative of the second function is 1/2. Evaluate, I have to use the chain rule, evaluate it at the inside function to the -1/2, times the derivative of the inside function, which is -2x. Okay, so now what I want to do is I would like to simplify this as much as I can. And so what I'm going to do here is I'm going to switch that back. I think it'll be easier to deal with it like this. And this then becomes minus, the 2's cancel out, but then I get an x squared over, and then this is square root of 9 minus x squared. So you get something that looks like this. Okay, and so now I want to multiply the top and bottom by this denominator here. Right, and then I'd get 9 minus x squared over square root of 9 minus x squared minus x squared over square root of 9 minus x squared. So this is just getting a common denominator. Now I can subtract these two, and I'll really, on the top, I'll get 9 minus 2x squared over square root of 9 minus x squared. Okay, well, this is the derivative. So now the derivative is going to be equal to 0 either when that numerator is equal to 0, okay, or this will have a critical point either where the numerator is equal to 0, because that's where the entire fraction is equal to 0, or it'll have a critical point when this is undefined. Now notice it's undefined at -3 and 3. Okay, so that we're not gonna, those are the endpoints of the interval. And so we're gonna check the endpoints, but we're not gonna consider those as critical points, okay, because they're the endpoints of the interval. So so I just need to solve this. So I get this will be 3 plus square root of 2x, 3 minus square root of 2x is equal to 0. So either we have this 3 plus square root of 2x is equal to 0. So x will be equal to negative 3 over the square root of 2. And then I'm going to rationalize the denominator just because that's what feels right. You wouldn't have to, but I'm going to do that. This one will just be the positive. So you have this one, you have x is equal to 3 square root of 2 over 2, the positive. So these are the critical points. So now I can set up my intervals. And so we have negative 3 to negative 3 square root of 2 over 2. And then we have negative square root of 3 over 2, or I'm sorry, negative 3 square root of 2 over 3 to 3 square root of 2 over 3. Sorry, that looks so messy. And then we're going to have the 3 square root of 2 over 3 to positive 3. Okay? So now we want to check the derivative at test points. Now this thing here is like, I don't know, negative 2.12 or something like that. And so what I'm going to do is I'm going to pick a test point, x is equal to negative 2.5. There's really no nice test point here. Okay, so you're just going to have to plug that in, and when you do, the derivative is actually equal to like negative 2.11. So it's negative here. So in here, the best point is choosing 0. And that's inside. And so when you plug in 0 here, this just becomes 9. This becomes the square root of 9, which is 3. And 9 divided by 3 is 3. So this is 3, and that's positive. And then I'll put in a positive 2.5. And notice, negative, positive, you'll get the same thing because you're squaring the x here. And so f prime of positive 2.5 is also negative 2.11. And so the derivative is negative. So this thing is going from negative to positive. It's going from decreasing to increasing. So you're going to get a max here at 2. And then here it goes from increasing to decreasing. You get a min here at and I said 2, I mean negative square root of 3, I'm sorry, negative 3 square root of 2 over 2, and then a min at positive 3 square root of 2 over, positive 3 square root of 2 over 2, sorry. This should be 2. I did this all wrong. I am so sorry. There. That's such a weird number anyway. Okay. So, to find, these are the relative min and maxes. Now, to find the absolute min and maxes, all I need to do is check this at the endpoints and at these points here. So I'm going to do this, check f at negative 3. Now I'm plugging them back into here to see which one's biggest. Well, this one you get 0, right? And then f of, I'm going to do negative 3 square root of 2 over 2 So I'm going to just plug that into here. So negative 3 square root of 2 over 2 times the square root of 9 minus negative 3 square root of 2 over 2 squared. When you do that, it actually equals negative 4.5. And so this is negative 4.5. So that turned out nice. And then notice if I put in the positive 1 here, that would be positive and this would be positive, but this doesn't change. And the only thing that's going to change is the sign. Okay? So this would be 4.5. And then f at 3 is going to be 0 again. So it looks like this is the absolute min, and this is the absolute max. They're the relative min and max and the absolute min and max. And so we figured all that out without graphing it or anything. So now let's graph it and see what we get. X times the square root of 9 minus x squared. And I'll do this on a standard window. And sure enough, we got a relative min, relative max. So let's put in our critical value. So negative 3 square root of 2 divided by 2. Let's see if that's the relative min. And it is. And then the other one should be the relative max. 3 square root of 2 over 2. And there's the relative max, which also happened to be the absolute min and max over the interval. So that's an interesting looking function. And notice we were able to tell all of that using the calculus, using the first derivative test and everything. So this calculus is a very useful tool.